Covalent bonding is a phenomenon that arises from a sharing of electrons and a shared pair of electrons constitutes a bond. When we see covalent bonding is when elements that are making a compound have similar electron affinities. It occurs when a complete transfer of electrons is not likely, and the reason is it's not likely is because the elements involved have similar electron affinities. So we have an atom achieving its noble gas configuration, much like what we saw with ionic bonding, but we're going to do it by sharing electrons. So sharing a pair of electrons constitutes a bond, and that sharing of electrons is happening rather than a complete transfer of electrons because the things involved have similar electron affinities. I'm going to get the periodic table. As you recall from ionic bonding we had a metal binding to a non-metal, and that's when we had a metal with a low with an ionization energy and electron affinities that are favorable to make a transfer of electrons. With elements up in this area that have similar electron affinities, and mainly where we'll see covalent bonding is with elements in this area right here, indeed. So nonmetals is where we really see covalent bonding the most. And the reason so in other words, sulfur and oxygen, or nitrogen and oxygen, or carbon and nitrogen, or chlorine and nitrogen, when those things form bonds, they have very similar electron affinities, and so you will have a sharing of electrons rather than a transfer of electrons. Let's look, for example, at some terminology, and I'm going to start to, so let's look at chlorine. The way we would draw the Lewis structure for the chlorine molecule, would be like this. And I'm going to show you how to do Lewis structures in the next lecture, but for now just accept the fact that this would be the correct Lewis structure for chlorine. If you're not sure how this came about, don't worry right now. We're just talking about terminology. This is another way to illustrate the Lewis structure of chlorine. Right here, we have a bonding pair of electrons. And the bonding pair of electrons is between the atoms that are bonded together. Oftentimes, we'll use a bonding pair of electrons. We'll show a bonding pair of electrons with a line rather than two dots. But anyway, these are called bonding pairs of electrons. These electrons here are examples of what are called lone pairs of electrons. And what's happening here is that both chlorines are essentially contributing an electron to the bond, and the other electrons are non-bonding electrons. Lone pairs, non-bonding, or non-bonding electrons. Okay. Now, so what's happening here is each one of the chlorines would donate one electron to make this bond. There's also another, just as almost an aside, there's also something called a coordinate covalent bond. where so what's happening up here with chlorine is we have something like this happening. We have each one of the atoms bringing an electron to the table to form the bond. With a coordinate covalent bond, both electrons of a bond are donated by one atom. It's a little rarer. So in other words, we might draw a picture that looks something like this. If we use this as an analogy, it might look something like this. So we still have a covalent bond. There's still a sharing of electrons. But one of them is donated by both atoms. Here's an example of a coordinate covalent bond, a compound that does this. So this is a coordinate. If we have boron, trifluoride, its Lewis structure would look like this. And again, don't worry about how I got this. This is the Lewis, trust me on this. I'll show you how to do Lewis structures in the next lecture. But what happens if boron trifluoride reacts with this molecule called ammonia, what's happening is we have a bond between the boron and the nitrogen. But both of the electrons that are part of the bond come from the nitrogen. Okay, so that's just it. So I want you to be aware that there's such a thing as a coordinate covalent bond. Okay, we talked about the octet rule. And we'll use the octet rule we briefly introduced it, but I want to define it now, and this is except for hydrogen, atoms tend to form bonds until they are surrounded by 8 valence electrons, or 4 pairs of electrons. 8 valence electrons or 4 pairs of electrons. So as an example, if we have a selenium atom, it has 6 valence electrons. How did I get that? Let's go back to our periodic table, find selenium. We're going to count 1, 2, 3, 4, 5, 6 valence electrons. 1, 2, 3, 4, 5, 6. These are so these would not be the valence electrons, the d electrons. We're talking about the s and p electrons for the main group. Okay, so it has 6 valence electrons, and we could ask how many H atoms would bond to one selenium atom. Okay, well, the answer would be 2. We could have essentially 2 bonds that are being formed because each hydrogen would essentially bring 1 to the table. So we can have these type of things, and this would be something called this is a single bond. Right? We have 1 pair of electrons that's constituting a bond between those 2 atoms. All right? To ensure that the octet rule is satisfied, sometimes there are multiple bonds that are necessary to be made. So to satisfy the octet rule, more than 1 pair of electrons may be shared between 2 atoms. Okay, here's an example. And again, don't worry about how I get this. I'll show you how you would get these Lewis structures soon. But here are two examples where we have the Lewis structure for C2H4 would look like this. The Lewis structure for carbon dioxide would look like this. And what we're seeing here is that there are each carbon is the octet rule satisfied. Well, each of these bonds is 2 electrons. 1, 2, 3, 4, 5, 6, 7, 8. But to make it so that the octet rule is satisfied, we have to have a double bond there. Same thing for this. You'll notice that the octet rule is satisfied for all of the atoms in CO2 when we have double bonds to the carbon. The octet rule is satisfied for the hydrogen when we only have 2 electrons around it. We can also have triple bonds. So these are double bonds. These are triple bonds that are possible. Here are two examples. Nitrogen. Nitrogen's best Lewis structure would look like this, where we have 3 pairs of electrons that are being shared between the 2 nitrogen atoms. The best Lewis structure for C2H2 would look like this, where we have 3 pairs of electrons being shared by the carbon atoms. So those 2 are being shared by the carbon atoms, and then the octet rule is satisfied. Okay. One last topic with respect to covalent bonding is this idea of bond polarity and something called electronegativity. Okay. Let's first look at this idea of polarity, bond polarity. For 2 identical atoms that form a bond, the electrons are shared equally, and the bond is nonpolar. So, excuse me, I'm going to erase this. Okay, so for example, hydrogen has, H2 has 2 electrons being shared between those 2 things. Chlorine, its best Lewis structure, Cl2, would look like this. These two electrons, when you have the same atom being bonded to one another, those 2 electrons are essentially shared completely equally. And the bond is what we would call nonpolar. Okay, if atoms forming the bond are different, there is generally an unequal sharing of electrons. And the bond is what we would say polar. Okay, so identical atoms forming a bond, nonpolar. Atoms forming a bond are different, unequal sharing of electrons, and the bond is polar. So equal sharing nonpolar, unequal sharing polar. Let's just think of an example. I'll show you a couple of examples of this, where we would have a polar bond. If we have hydrogen fluoride, HF, the HF molecule, there's an unequal sharing of electrons between these two things, and the atoms sort of assume a partial charge. And the way we would illustrate that is by doing this. So we're just illustrating that, okay, if we have different atoms forming a bond, the bond is polar. How is the bond polar? Well, the fluorine has more electrons, is going to have more electrons around it. We would call it a delta negative charge, a small negative charge, whereas we'd have a delta positive charge on the hydrogen. We could do something similar with the water molecule. In this case, the oxygen is going to have a slightly delta negative charge. The atoms have assumed a partial charge of negative partial charge on the oxygen, whereas the hydrogens are slightly positively charged. Okay, well, how do we know which atoms are going to concentrate the charge if we have a polar bond? Well, that's a relatively easy way, and that's an easy way to do, and this is something called electronegativity. Electronegativity is the ability of an atom in a molecule. Note, an atom has to be in a molecule. Okay, electronegativity is the ability of an atom in a molecule to attract electrons. The way electronegativity works is this. It parallels electron affinity. So we can draw our little cartoon periodic table like this, and we have increasing electronegativity as we go from left to right in the periodic table, and increasing electronegativity as we go from the bottom to the top. So metals, least electronegative. Nonmetals are the most. Most electronegative. All right, so that's the trend that we need to know about. So for example, this would explain why we know that the fluorine would have a delta negative charge and the hydrogen have a delta positive charge. It is more electronegative, right? Fluorine is located here in the periodic table, hydrogen is over here. So it is more electronegative than the hydrogen. Same thing with oxygen. If we use our periodic table, oxygen is here, hydrogen is here. Oxygen is more electronegative than hydrogen. Fluorine is more electronegative than oxygen. Oxygen is more electronegative than nitrogen, and so on. Okay, so that's what the idea of electronegativity is. And so what we can say is that the degree of electronegativity depends on the magnitude of difference in the electronegativities of the atoms forming the bond. Okay, so we could have, say, for example, a bond that is non-polar. where we have basically an equal sharing of electrons. We could have where M is a metal and X is some nonmetal. So we could have a polar bond where we have greater amount of electrons around the more electronegative atom, a metal and a nonmetal. We could have, on the other extreme, we could have a complete transfer of electrons, where we would think of as an ionic bond. So we can think of bonding in one sense as almost a continuum of going from a nonpolar equal sharing of electrons to a total transfer of electrons. So that we'd say is that, yeah, the greater the difference in the electronegativities, the more polar the bond.